machine learning technique, but it's not new. The first paper was actually 1991, so that's like a good amount of time. But the reason it's so relevant right now and the topic of discussion in the ML community is all because of deepseek. I don't know if you guys remember, but in 2024, deepseek released their V3 model and then followed by their R1 model. And these models basically broke the internet and dropped OpenAI share by 20%. Right? The reason they did this is because if you look at ChatGPT's GPT-4, it took them around hundreds of millions of dollars, while DeepSeek did it in $5 million. ChatGPT took 6 months to train, they did it in 55 days. There's a major difference between this, and the reason they accomplished all of this is thanks to mixture of experts. Their entire model is based on mixture of experts. So, what is mixture of experts? So, mixture of experts is a technique where specialized sub-networks, experts, are activated instead of activating the whole model. Slightly technical, but let's break it down. Right? Let's start with these sub-networks or experts. So, what are experts? Now, think about it like this. If I give you a task, you're going to run it through your entire head, right? And you're going to give the output. That's what the machine does. In GPT, when you give it an input, it runs it through its entire model, gives you an output. Now, think of it like this. If I tell you to go find a person, and I tell you they're in the engineering block, you're going to search all floors, all classrooms to find this person. But what if I tell you they're on the 3rd floor? You just search the 3rd floor, right? So it's very specialized. So you're activating only the 3rd floor. That's kind of what MoE does. It breaks down its main network into sub-networks. And those sub-networks are activated based on your needs, based on the inputs. So only one specific network or few networks are activated based on the needs. Alright? Now, what did DeepSeek do differently? It's been around for a while, I'm sure experts. What DeepSeek did differently is essentially they blew the proportion of the number of experts they have. Consider this, you have a football team, you have 4 players, you have a striker, 2 defenders, and a goalkeeper. They'll work, they'll play. But that one striker has to focus on the entire thing, right? But let's say you have a team of 11, you have 3 strikers. Now one striker can focus only on the right side. So the number of experts improves. So what DeepSeek did is, the standard MoE, the one in 1990s, and the ones that we have learned until now, had only 8 experts. DeepSeek grew that to 256. That's a very large number. So now each of these 256 experts can focus on one very, very niche topic, and they are activated when your input gives something similar to that. There's also something called shared experts. Think of shared experts as the experts that will always be active, like your team captain or your star players, the ones that will always be on your team. These are the ones that will help you understand your input before moving it forward to the next networks. This is the basic design of an MoE, and what I'll be breaking down today. It's actually very simple. You have the input, what you give your model, the output what the model gives you, and there's just one MoE layer. And the MoE layer just has 2 things. It has the router, so the gating function, which I'll get to in a second, and then you have the experts, right? So let's break it down one by one. You have the router of the gating function. You have 256 experts. You're not activating all of them at the same time. Who decides which ones to be activated? Well, that's your router or gating function. That's like the coach of the team. You look at the opponents or your inputs and you decide your experts based on that. There are a few conditions that every router function must understand, must complete to actually be a proper router or a gating function. The first one is it must understand the input and it must understand the experts. That's basic sense, right? It needs to understand what you are giving it and what it has to actually compare it. The second is should be evenly distributed to avoid model collapse. I'll get to model collapse in a while. That's basically the biggest flaw of an MoE. We'll get to that in a minute. These are 3 types of gating functions. Alright, the first one is linear gating, and it uses softmax. It's also known as a softmax gating function. What it does is your G is your input, right? It takes top K. Top K is as in you give K a value. So let's say you have 100 experts, and I tell you I need only 2 experts. So you take the 2 most relevant experts, okay? And you give them a certain score based on their relevance. One will be more relevant than the other. You take the remaining 98 and you give them a score of -infinity. And then you pass it to a softmax function. Now what a softmax function does is all the K experts that you have, it brings them into probabilities of 0 and 1. So they add up, like probabilities do. So once they are -infinity, you get a probability of 0. So they don't pass on, so you don't activate those functions. And that's basically gating. Non-linear gating function, also known as cosine gating function. What it does is it projects your input in a hyperspace. And it does the same thing with their experts. And then compares the angle between these two. I don't know if you guys remember, this is the vector angle, the cosine angle from vectors. then it looks it's like, so this is the one that has the least angle, so it's the closest to our input. And then it activates based on that. Again, it uses the top case, so essentially it will take only the ones that are close and the ones you require. If you require any k experts, it takes the 8 closest experts. Sequence gain is slightly different, and it is the one that deepseek actually uses. Now, there's a problem with the linear gain. If I want to increase the expert value for one of them, I have to decrease it for another one of them, because probabilities must add up to 1. But that's not the case with sequence. It also reduces everything from 0 and 1. But that 0 and 1 does not depend on any other. They're all independent. So I can have multiple important experts, rather than just one very important expert, and like all of them coming in the probability scale. That's pretty much all I have on gaining functions. Expert level, the second most important part, essentially the heart of it all. There are two ways, two most popular ways that we do it. Well, the first one is replacing an FFN layer with the MoE layer. I will use chalk over to explain this real quick. Well, if an FFN layer, you have a lot of neurons, alright? And when you pass in your input, the input connects to every single one of these neurons. So you go like this, you go like this. Now that's very computationally heavy. You're connecting every single one of these neurons. Some of them are not necessary. So what we do is we take this and make it much smaller. So you have like a much smaller FFN layer. And it's all connected in this, that's fine. But what we did is we broke down an FFN layer into small layers and we activate the FFN layer depending on our requirement. So you may not necessarily activate all FFN layers. So let's say you have 10 and you're using only 2. The remaining 8 are not consuming any energy. So that saves a lot of computational costs. That's not the whole point of deepseek, it's to reduce computational costs. The second is applying the MoE to the attention module in transformers. So if I give you a sentence, what a transformer does is it assigns attention based on relation to every single other word. So if I tell you, the boy played a game, he is tired, it will keep assigning every single word and keep relating it with every other single word until it comes to something like he and boy and it relates it, then these two are the same thing. That's fine if you have a sentence, right? But we don't really deal with such small data sets. It's a much larger data set. So what actually happens is it gives an expert networks. So one expert network will only focus on the linkage between, let's say, verbs, or one will focus only on words like and the. And it gives these words like a smaller expert network. Right? That's expert networks. Routing strategy. Well, the routing must be important, right? We have to activate the right experts. The routing strategy and the routing training is very important. How do we activate the right experts? Well, you tokenize. Every machine learning model uses tokenization. You have two types of tokenization: text tokens and patch or image tokens. So there are two different methods it uses. So text tokens use something known as mass tokens. Now what it does is it takes a word and it doesn't show you what experts are, and it just assigns it the expert. So let's say you have a word that keeps coming way too many times. We'll assign it to multiple experts. This is done to understand the word better because it's showing up so many times. Let's say I have bank, and bank could be the bank, the money bank, or river bank. So we'll assign it to 2-3 different experts so we can understand all the meanings of it. But if you have a very specific word that has no other meaning, it assigns it only to one expert. It uses RNN to hold the memory because it needs the memory of how many times it's been assigned and where it's been assigned. Moving on to patch tokens, patch or image tokens, you take your image and that's split into multiple tiny patches. And then each of them are calculated and given a score or an importance, and that is put in a descending order, and based on that descending order, we assign experts. Model collapse. Everything we got about MoE sounds very nice, it's too good to be true. But the biggest problem with it is model collapse. What really happens and why it took so long for people to figure this out is you're in a class, okay? The teacher is, let's say, the gating function, the students are the experts. The teacher calls upon a student to answer. The student answers, the student learns, right? Let's say you're a student who doesn't get called upon at all. You are not learning anything in that class. If you're not learning, that causes a very big imbalance in the model. This is the biggest problem with MoE. The imbalance causes the model to just collapse. That is kind of what they figured out. They solved by switch transformers. You also have expert capacity. So you have a lot of data on math. So you keep giving input of math. you're not going to keep passing on to your math expert. Your math expert will get overwhelmed, will get tired, it just doesn't need all. So what happens is after the expert limit, it basically just stops sending that, all that. It just processes it like this without anything, or it drops it. Both cases can happen. If you look at switch charts, this is a slightly complex equation. F is the workload of your expert, and Q is how much your model wants to send the expert, send the data to the expert. Even if it doesn't send it over there, how much it wants to send it to. And the product of these two is essentially what penalizes your data state, right? N is the number of alpha is how much your model actually cares about balancing. So if alpha is 2, that's your model does not care about balancing anything. And what it will do is it just assign random stuff. And if it doesn't care about balancing, the model will collapse. Now imagine alpha is too high. Your model cares only about balancing stuff. Now if it cares only about balancing, let's say your math module hasn't got any data in the file, it will send a wrong question to the math module. That's also not good. It will drop your accuracy. So alpha is something that really needs to be maintained in the middle, and that's kind of what deepseek did well. They figured out how to hold their alpha as the right value. That was pretty much the talk. My next step would be reading hierarchical MoE. It's another type of MoE. I'll be working on that. If you found this interesting and if you had fun, you can check out my blog. I made a blog post on this. It's a lot more detailed. And anything else I will be doing, like reading the hierarchical MoE, will be on the blog as well. I'll be updating that. Any questions, guys? Any questions? I just put the link. Actually, this was today morning. I realized I should probably link that because I will be working on it, and everything I update will be going on there. This is the blog that I think I have. Yeah, this is the blog. It's a lot more detailed than the blog, but it essentially covers the same things. And it also has references that I use to understand this. This is a very, very nice paper. It's comprehensive guide to MoE. It's a very long paper, but it references every single MoE module. It was at least 2 months old, so it's very new. It references everything. It's a very well written blog. If you want to get started in MoE or learn a little more about